Good afternoon, students. Today, our topic of discussion is Maxwell's inductance bridge. Okay, why we need Maxwell's inductance bridge? Here we are measuring the value of an unknown inductance with the help of a standard inductance. Okay, so measures an unknown inductance by comparing it with a known inductance or a standard inductance. Now let us consider the circuit of Maxwell's inductance bridge. Well, this is the circuit of Maxwell's inductance bridge. It has four arms, arm AB. Here in arm AB we have a resistor Rx and we have a inductor Lx, and this is the unknown inductance Lx, and in arm BC we have a non-inductive resistor, that is R3, and in arm CD we have a non-inductive resistance R4, and here in arm AD we have a variable resistor R2 in series with a variable inductor L2, which is having a internal resistance of small r2. This variable inductor will be having a internal resistance that is represented by small r2, and we have given a AC supply to the circuit, and we have a detector which is placed in between. Now, how to balance this bridge? Right? How to balance the bridge? For that we have an equation, that is when the impedance of this arm, that is the impedance of this arm is Z1. This is the impedance of arm AB. This arm and this arm, the product of these two impedances Z1, Z4 will be equal to the product of these two arm impedances Z2 and Z3. So this is under balanced condition. This is the balance equation. It is Z1, Z4 will be equal to Z2, Z3. Now what is Z1? That is impedance Z1. Z1 is nothing but Rx plus j omega Lx. Rx plus j omega Lx. This is for impedance Z1. Now what is Z2? R2 plus this R2 plus j omega L2. This is the impedance of this arm AD. Now what is Z3? This is Z3. Z3 is equal to R3 and Z4 is equal to R4. Now we got the values of Z1, Z2, Z3 and Z4. Let us substitute in the balance equation, or that is Z1, Z4 will be equal to Z2, Z3. So this is Z1 Rx plus j omega Lx, and this is Z4 which is equal to Z2 is R2 plus small r2 plus j omega L2 into R3. So let us multiply this Rx into R4 plus j omega Lx into R4, which is equal to R2 plus R2 into R3 plus j omega L2 into R3. Now here, after this equation, we should separate the real parts as well as imaginary parts. Now let us equate the real parts and imaginary parts. If I equate real parts, this and this I should equate, and imaginary parts, this part and this part I should equate. So I have considered those equations. Rx, R4 is equal to R2 plus R2 into R3. I need the value of Rx, unknown resistance, right? So Rx will be equal to R2 plus R2 into R3 divided by R4. This is the value of Rx. Now we got the value of Rx. Now if we equate imaginary parts, j omega Lx R4 is equal to j omega L2 R3. J omega gets cancelled, and Lx will be equal to L2 into R3 divided by R4. This is the value of unknown inductance. So from this method we have found the value of unknown inductance. So right now we have got the value, that is Lx is equal to L2 into R3 by R4. What is this? This L2 is the standard inductance. We are finding the value of unknown inductance with the help of or comparing it with a known inductance, or it is also called as standard inductance. Now after this, the next major part is its phasor diagram. How to write the phasor diagram for this Maxwell's inductance bridge. So before writing the phasor diagram, we should analyze the circuit a bit. We should analyze this. The thing is, here we have a resistor, right? What is the voltage drop across this resistor? The voltage drop across this resistor will be I1 Rx, and what is the voltage drop across this inductor? I1 omega Lx. This is I1 omega Lx, voltage drop across this inductor. Now what is the voltage drop across this resistor? I3 R3. Similarly, what is the voltage drop across this resistor? It is I4 R4. Now when we come to this end, we have the voltage drop across this variable resistor is I2 R2, and here what we have? I2 small r2, and then I2 omega N2. Okay, because this variable inductor will be having a resistance R2. So I2 R2 is the voltage drop, and I2 omega L2 is the voltage of this variable inductor. Okay. Now we know that under balanced condition, the potential drop across this arm will be equal to the potential drop across this arm. So what is the voltage? That is E1 will be equal to E2 and E3 will be equal to E4. This is when the bridge is balanced. So what is the expression for E1? E1 is the potential drop across the arm AB, right? So what is that E1? E1 is nothing but I1 Rx plus I1 omega Lx. The same thing we have written here. That is E1 is equal to I1 Rx plus I1 omega Lx. Similarly, when we go to the arm AD, there in the circuit arm AD, E2, we can find out E2. E2 is equal to I2 R2 plus I2 R2 plus I2 omega L2. Under balanced condition, we know that the potential drop across the arm AB will be equal to the potential drop across arm AD. Similarly, the potential drop across arm BC will be equal to the potential drop across the arm CD. So under this condition, E1 will be equal to E2 and E3 will be equal to E4. Okay, under balanced condition. Now we have another condition. When the bridge is balanced, no current flows through the detector. Right? When the bridge is balanced, no current will flow through the detector. When no current is flowing through the detector, whatever the current which is coming in this arm will flow in this arm, and whatever the current which is coming in this arm will flow in this arm. That means the current I1 will be equal to the current I3, and the current I2 will be equal to the current I4. The same thing we have represented here. I1 will be equal to I3 and I2 will be equal to I4. Now how to write the phasor diagram? Let us fix I1 as our base. Okay, so let us take this arm as our base and we'll start writing the phasor diagram. First I will be fixing I1 as base. Okay, And before analyzing this, I wanted to tell you one more concept. If the circuit is resistive circuit, see, if the circuit is resistive circuit, then voltage and current will be in phase with each other. If the circuit is inductive circuit, if the circuit is inductive, then voltage leads current by an angle of 90 degree. If it is a capacitive circuit, voltage lags the current by an angle of 90 degree. So we should know all these three parameters while analyzing the circuit to write the phasor diagram. Now first, this is a resistive, right? Completely resistive. So what is the voltage drop here? I1 Rx. If current is in this direction, where should be the voltage? The voltage drop I1 Rx should be in phase with this. So I will write here as I1 Rx. Under balanced condition, we know that E1 will be equal to E2. If this E1 is equal to E2, I1 Rx will be equal to what? I2 R2 plus I2 R2. Are you getting this? This I1 Rx will be equal to, this will be equal to R2 plus R2 into I2. This will be equal to this current. Okay, and now next we have a inductive circuit here inductive circuit. The voltage drop here is I1 omega Lx. First we have completed this, next we are shifting to this. So I1 omega Lx should be perpendicular, that is 90 degree to the current, right? If this is the current, where should be the voltage? It should be 90 degree leading, right? So here I will be getting I1 omega Lx. So this is my I1 omega Lx, which is 90 degree to this. What is the resultant? I1 Rx and I1 omega Lx. The resultant of these two will be E1, right? So the resultant of this will be my E1, and this E1 is also equal to E2 under balanced condition. If E1 is equal to E2, I1 omega Lx, see this I1 omega Lx will be equal to I2 omega L2, because E1 is equal to E2, right? So this value will be equal to I2 omega L2. Clear? So we have analyzed this arm. Now from the balanced condition, we also know that the current I1 will be equal to I3. So what I can write? This is equal to I3. Current I1 is equal to I3. If I am having the current I3 here, okay, the voltage drop across this I3 R3 should be in phase, because we are having only a resistive circuit here. So the voltage drop should be in phase with this current I3, right? So where I have written I3, in the same line I should write the voltage drop I3 R3. So here this is my I3. So what I will do? I will write here, this is the voltage drop I3 R3. Okay. Next, the current which is flowing here is, this is I1 Rx, which is also equal to R2 plus R2 into I2. So even the current I2 is in this phase only. If current is in I2 is in this phase, then even I4 should also be in the same phase, because I2 will be equal to I4, right? So here this is, and right here I2 is also equal to I4. I2 is also equal to I4. Then where the voltage drop across this resistor I4 should come, I4 R4, it should be in phase with I4, right? So this is I4, and this, where I am having I2 here, this is also equal to, this is also equal to I4 R4, I4 R4. Okay. So now this I3 R3 is equal to E3, right? This is equal to E3, and this E3 is also equal to E4 under balanced condition. This is also equal to E4 under balanced condition. Now if you observe here, at this point I am having E3 and E4, and at this point I am having E1 and E2. Now if I take a resultant of these two, then I will be getting the supply voltage, that is this E, because this E will be equal to E1 plus E3 or E2 plus E4. So I will write here the final expression: E is equal to E1 plus E3 or E2 plus E4. E1 plus E3 or E2 plus E4. Now this is E4 E3 point, and this is E1 E2 point. I should write a resultant for this. So let us extend this, and let me extend this, and the line which I draw here should be parallel to this. So here we get the resultant waveform. This is E, which is equal to E1 plus E3, or which is also equal to E2 plus E4. That's it. This is how we analyze the phasor diagram with the help of the circuit. Clear? Thank you.